Our focus here is going to be using what are known as integration tables. And we're told to use the table of integrals in the back of the book to evaluate the integral of the square root of 2y squared minus 3 divided by y squared dy. If we worked really hard at this, we could probably find a way to do this using trig substitution. However, somebody already has, and they've figured out how to express something like this in general, and they wrote it down for us. In the reference pages in the back of the book, you'll find algebraic formulas and geometric formulas, trigonometric identities, some graphs of various functions, polynomials, exponentials, logarithms, hyperbolic functions, and differentiation formulas. But there are also a bunch of integrals. This is a table of integrals, as you can see. The first chunk of the integration formulas are the ones that you've learned throughout the first semester of calculus and this course here. Then we see that they're classified according to form. We have forms involving the square root of a squared plus u squared, a squared minus u squared in a square root, the square root of u squared minus a squared, forms involving a plus bu, trigonometric forms, almost an entire page of these, inverse trigonometric forms, exponential and logarithmic forms, hyperbolic forms, and finally forms involving the square root of 2au minus u squared. Folks, there are 120 of them at the time that this video has been made in this book. There are bunches more out there that people who do this for a living actually use. Our task is going to be to compare what we have with what's in the tables. So what we have here is a square root of 2y squared minus 3 divided by y squared. I see that what we have in the square root is a first term that has a y squared and then a second term that's a constant. And so I'm going to look for the various forms that we just went through. And I see here forms involving a plus bu. That's not what I'm looking for. U squared minus a squared. I think this is what we want. Folks, our choices were square root of a squared minus u squared, square root of a squared plus u squared. But I think that the square root of u squared minus a squared best fits what we're looking at over here on the left. If we are indeed looking at a square root of u squared minus a squared, then it must be the case that u is equal to the square root of 2 times y, and a is equal to the square root of 3. Notice that each of our forms also has a du. That shouldn't be surprising. Therefore, having identified u as the square root of 2 times y, we know that du is equal to the square root of 2 times dy. I'd like for you to take just a moment and scan the portion of the table that is on the screen now and see if you can identify which form we're going to be using. Just pause the video and do it. I hope you actually did that. And it turns out we're going to use this form here. It's number 42 at the time that this video has been made. I don't know if they're going to revise this in future editions. But what we see here is the integral of u squared minus a squared in a square root divided by u squared. That's the closest match to what we have over on the left. I'd like to trade out the various pieces that we have in our integral so that we can write it in terms of u. We have a good portion of that already done. We know that 2y squared is going to be u squared. But then what's y squared? Well, since u is square root of 2 times y, we know that u squared is equal to 2y squared. Here's the way I see it. In order to have du, we need to multiply dy by the square root of 2. So I'll move dy over and multiply it by the square root of 2. If we multiply by the square root of 2, we must divide by the square root of 2. In order to have a u squared, we need 2y squared. Therefore, in the denominator, I need to multiply by 2. That's really dividing by 2, and so out front I'm going to multiply by 2. 2 divided by the square root of 2 simplifies to the square root of 2. The rest of the integral we can write in terms of u. We have the square root of u squared minus 3 divided by u squared du. Now that we have that straightened out, let's see what the integral evaluates to on the other side of the equal sign on the right-hand side. We have negative square root of u squared minus a squared over u plus the natural log of the absolute value of u plus the square root of u squared minus a squared plus c. That's quite a bit to write, but we're mostly going to be copying and just replacing as we go. So our integral then becomes the square root of 2 times negative square root of u squared minus 3 divided by u plus the natural log of the absolute value of u plus the square root of u squared minus 3, close the parentheses, plus c. Our original exercise was given in terms of y, and so we need to express our answer in terms of y. Back substituting, we have the square root of 2 times the quantity of the negative square root of 2y squared minus 3 divided by the square root of 2 times y plus the natural log of the absolute value of the square root of 2 times y plus the square root of 2y squared minus 3 plus c. And we're going to take one final step because we can simplify the square root of 2 out front and in the denominator of the first term. So we end up with the negative square root of 2y squared minus 3 over y plus the the square root of 2. Forgot we were distributing there. Times the natural log of the square root of 2y plus the square root of 2y squared minus 3 and absolute value plus c. And look at that, I forgot to end the absolute value in both of the previous steps. There we go. That's our final answer.